Hey, what's going on, everybody? This is JJ, and in today's video, I want to run through an introduction to chemistry, and I actually am going to begin with, I should say, fundamental physics concepts that I think are necessary to learn before you even begin studying chemistry. Before I even do that, though, I want to run through a framework I have for pursuing knowledge through independent study and the linear approach I think one should take to do it. And the first thing you should learn as an independent intellectual is studying mathematics. Mathematics is a way of thinking. It's how you orient your thinking in a logical manner. It is the language that describes how the universe works. It's the language at least we humans deploy to understand it. And it's a standardized convention that transcends any dividing lines such as culture or geographical boundaries, language boundaries. Mathematics is the same across any of those different dimensions, and we can use it to understand the same concept in the same manner no matter who you are. And so mathematics serves as that fundamental foundation for all science, and it's also a way of thinking and orienting your thought process about how to interact with the world. The next level is physics, which uses mathematics and actually is just a mapping of mathematics onto the physical world we observe. We run through experiments, we can put together theories and formulate hypotheses, test those, and then we can generate a mathematical relationship with that phenomenon and see if it holds true consistently and irrefutably. And that way, if it is refutable, then that means we are able to falsify that theory and we can reject it and move on to a different one that is more accurate description of reality and the physical world we live in. The next level is chemistry. Chemistry builds on the foundations of mathematics and physics, although the mathematics doesn't get too complicated. But understanding some of the some of the important concepts in physics, which we will run through in this video, is a necessary precursor to understanding chemistry. But chemists use elements at a level that allows us to perform reactions and experiments with different substances and mixtures, so that we can make new medicine and have a better understanding of how the elements that make up our universe interact with each other in a way that we can use and benefit from. And then the next level is biology, which again builds off physics, mathematics, and chemistry in order to understand life and the life sciences. The last layer will be cosmology, which is, I'm not using it in its strict definition, but I'm using it to encompass basically everything from the Big Bang Theory to the multiverse to black holes to galaxies and the relationship between all the planets and the universe, along with, relativity and quantum mechanics. So a really all-encompassing term there that I throw in. And then we understand each of these different scientific domains through technology. At least we better understand them through technology. And lastly, we have philosophy to put all of this knowledge into perspective and give meaning to that knowledge for human beings and why we should care and how we should orient ourselves in our lives and in the universe. And so that's my framework for pursuing any intellectual endeavor, whether independent or dependent on some institution. So the first area I'm going to start out with before we can jump into chemistry is a few physics concepts. And the first one is atomic theory. And a man by name John Dalton came along and gave us really the first conceptualization of the atom. And he said that the atom was the most fundamental particle in the universe. It could not be divided any further, and it can make up a whole number integer ratios with different elements to form chemical compounds. And unfortunately, he was incorrect in his first assumption that it was the most fundamental constituent of matter. We do now know that there are many different particles that even make up the atom. And so he was wrong there, but he was correct in his law regarding whole number integer compositions of different elements in a compound and the relationship between them. Then came J.J. Thomson. J.J. Thomson wanted to build on John Dalton's framework for the atom, and he actually discovered the electron. And the electron was actually the first particle to be discovered, and he used a cathode ray to do it. And the cathode ray is really just a beam of electrons, and he gave us the name electron. The cathode ray was discovered before J.J. Thomson used it. However, he pioneered our understanding of it further and gave us a fundamental particle we call the electron. Unfortunately, JJ also gave us a model for the atom that was also incorrect. He called it the pudding-like model, or something similar to that phrase, where it was really just a nebulous cloud of electrons. But then Ernest Rutherford came along and really proved that, or falsified that model or theory by showing that if you shoot an alpha particle at an atom, that if JJ was correct, that atom should move unscathed right through the atom. It should not be influenced in any meaningful way as it moved through the atom. But as a result of an experiment Ernest did, he showed that there was actually 4 separate outcomes of varying degree when he shot an alpha particle at an atom. The first one was, yes, it did go through the atom unscathed, but the other 3 were much different. They could either have the alpha particle would either slightly deflect in another direction, it could significantly deflect in another direction, or it would even reflect, meaning it was sent right back from where it was shot from. And this demonstrated that there is something actually going on in an atom beyond just the electrons. And then that's how we got the nuclear atom theory, where the nucleus is at the center of an atom with the surrounding cloud or wave function of the electron, and that nucleus is made up of a positive proton called the proton, a positive charged particle called the proton, and a neutrally charged particle called the neutron. And so now we have that nuclear atom theory, and we use it to this day. But beyond just the atomic theory, we actually now have a standard model of elementary particles that go well beyond the atom, and we call it particle physics. And you should have a high-level understanding of particle physics just to know, the framework maybe, and how there exists many other particles and relationships that go beyond the proton, neutron, and electron. And then you can build up an intuition for what's happening in chemistry. Here are some images of atoms that I could find. Scanning tunneling microscopic image of gold atoms on a gold surface. Looks like this. It's pretty cool. Get a little shape, little hexagon shapes almost. And then here is the world record for resolution of an atom, of atoms. I don't know what the element is, but I do know that it is at the picometer level, so 10 to the negative 9th in meters. And so here, this looks like maybe neutrons, protons, I'm not sure. And then, yeah, pretty cool image. And then I did do a cool video on matter, which we are going to run through in this video, and also atoms and atomic theory. And you can find the video called "At All That Matters in Our Observable Universe," it's called, at Piazza Research. So do check that out. It's a very short, cool video, creative video. And then one more physics concept I think is necessary to study before jumping into chemistry is electromagnetism, and specifically electrostatic forces, which is at the fundamental relationship between like charges and opposite charges, which really make up the mechanisms for bonds between different elements. And then those bonds form compounds, and then those compounds can react with other compounds to make different reactions that we study in stoichiometry, which is at the end of this video. And so understanding electrostatic forces, which we call Coulomb's law, a formulaic expression that describes the relationship between charges expressed in coulombs and meters. And so we have the net force is a result of the some constant of two charges multiplied the product of two charges over the radius squared, or the distance squared between those two charges. And so that makes up the relationship of electrostatic forces, which is awesome, and it was named after Charles Augustin de Coulomb. We also know that any given charge has an electric field around it, where any point in space has a vector that describes the magnitude and direction of the force at that given point in space. And so you can imagine another point charge entering the electric field of a different point charge, and then that point charge will experience whatever vector is at that point in space. And then the point charge that came into the picture would also have its own electric field, which would interact with this point charge. And so that forms an interesting relationship between all of the different electrons and particles out there that have charge. And lastly, there is this cool concept called magnetic field, which is very similar to an electric field, just that a current is moving through space, so electrons or charges moving through space can generate a magnetic field instead of an electric field. And so that's electric magnetism at a high level. So those are the three concepts: atomic theory, particle physics, and electromagnetism are necessary, in my opinion, concepts to understand before jumping into chemistry. And so what is chemistry? Well, it's the study of matter. And matter is made up of mass and volume. So anything that has mass and volume is considered matter. And we measure mass in grams and moles, and then we also measure volume in meters and liters. But chemists needed to develop a unit to understand atoms and molecules at a macroscopic level, because that's where we live. We live at the macroscopic level, and we interact with compounds and substances at a macro level. And so chemists developed a unit called the mole. And the mole is really just 6.022 times 10 to the 23rd, an unimaginably large number of atoms and molecules. And so this is a standardized unit that chemists use and deploy throughout their study of compounds and substances and the reactions they undergo. And so we can also use a mass spectrometer to measure a mole. We can measure the mass of this many atoms or this many molecules using a mass spectrometer. And the mass spectrometer produces a mass spectrum. And that mass spectrum could have varying different abundances of a given molecule, for example. So in this example, it's pentane, which is represented by this empirical formula. And so we have different outcomes that the spectrometer measured. And so the most common isotope, if this was just an individual element instead of a molecule, would be 43. And so that one is the most abundant. But you could imagine, let's say we were measuring carbon or oxygen. It has different isotopes, meaning it has more neutrons than it does protons. And so we want to know how often that isotope exists, and we would find the average between all of the different isotopes, weight them, and then we get our average atomic mass, which is always going to be this number at the bottom of a periodic table of elements. This represents the atomic mass unit, the average atomic mass, and is exactly 1 mole of argon. So 39.948 grams of argon is equal to 1 mole, and 1 mole, as we know, is 6.022 10 to the 23 atoms of argon. And so we could even extend this even further and imagine we wanted to know the mass of an individual atom for whatever reason. We would take the molar mass, so that 39.948, and we would divide it by the Avogadro's constant, which is another name for the mole. This is the Avogadro's constant, this number. I don't know if I mentioned that already. I think I forgot. And we can get the mass of an individual atom. And so that is mass spectrometry, and a little bit of an introduction to the periodic table, which I'm sure you're familiar with at this point. And then we can move into the different classifications of matter. There are pure substances and mixtures. Pure substances are just compounds or the individual element themselves, like in a hydrogen, oxygen, or carbon. Compounds are like H2O, NaCl, and sugar or glucose. And then we have mixtures, which are can be either homogeneous or heterogeneous. Pretty straightforward. Homogeneous just means the solution or alloy is the same concentration of a given element or compound at all points in the volume that you're sampling. And then heterogeneous has different compositions or concentrations within different regions of whatever compound or whatever substance you're sampling. And for example, dirt is different in certain regions than in other regions, and sand is different in other regions than other regions, and so on and so forth. And so we can make them up into two classes, pure substances and mixtures, which can further be classified into different sections. And all of that leads us to stoichiometry, which is really just the mathematical expression of chemical reactions and how different molecules and elements and compounds interact with each other to form important physical reactions in our daily lives or in our universe in which we can observe. And so one thing to quickly point out is that this is a very, very simplified chemical equation. They are much more involved than this, and it's a lot of math, but the math is pretty straightforward. It's just understanding what values to plug in where. It's mostly just algebra and maybe a little bit of geometry, but you don't need higher level math to do stoichiometry. Another important point is if you've ever seen a stick and ball model of different chemicals or different molecules or formulas, they have like this stick part. Well, the stick part is misleading and doesn't actually exist in reality. Once a atom bonds to another atom, they smush together. There's no like bar connecting them. They're just smashed together, and so these little dots are more accurate visual representation of what a molecule or compound or diatomic element. And so with that is chemistry, an introduction that I think is different and unique than most people teach it, but nonetheless still valuable to whoever took the time to watch this whole video. And so with that, I'll see you guys in the next video, and have a good one.